I'd like to recognize Dr. Hamad Abdelrazik, who did his PhD at Missouri S&T on the subject of research I'm presenting. He's now a professor at the University of Cairo in Egypt. So this work is dealing with material performance, construction performance, and some structural performance of high-performance concrete. That's what we call fiber-reinforced flowable or super workable concrete that is meant for bridge rehabilitation. This work was done in collaboration with Missouri DOT and the Tier 1 UTC, which we call RECAS, where Dr. Nassif participated very actively in this. I'm going to show you most of the presentation dealing with the repair of this bridge. So whenever a DOT gives you a bridge, it needs to be kind of a rural area and not a main bridge because they want to be very careful about the technology. So we got a bridge that was actually quite challenging with two spans that are quite long. You see here the lengths of the spans, 115, 125, simply supported on pre-stressed girders with the bridge deck being 12 inches with double rebars continuous. So as you would expect in the middle where the here is the bend, you'll expect a lot of negative moment with the concrete being in tension. And we had to take special measures to reduce the shrinkage of the concrete, but also when cracking does occur, to keep the cracks very, very small. And this is the deck condition, and we saw some nice examples from Colorado and from Michigan, so Missouri is not any different. This is an old bridge and has seen its service life and had to be completely reconstructed. So the first part of the project that we had was part, again, of a major effort working on the use of fiber-reinforced concrete for construction, for rehabilitation of various elements of bridges, vertical, horizontal, bridge deck, substructures. So that involved a lot of work, and I'm presenting few results about the performance of the fiber-reinforced super workable concrete. But the second part is dealing with the rehabilitation. So we call this bridge the Taos Bridge near Taos, Missouri. So we had to develop a special performance-based specification for the development and of these mixtures. So a special job provision, do the implementation, support the contractor, the owner, concrete suppliers throughout all the activities, do a lot of sampling, instrumentation, and modeling, and post-construction performance. Now here you have two columns, the first one in black showing the mixture proportioning of a fiber-reinforced self-consolidating concrete, and the one in red is fiber-reinforced super workable concrete. So what I'm presenting today is the latter. You can see in terms of water to binder ratios, they're both the same. So we want high performance. They're designed for durability and service life. And that's secured by reducing the water binder ratio, but also using a binder that will give you very good performance. So in this case, you see 25% slag cement and 5% silica fume versus 30% fly ash. In the Midwest, we have a lot of sea fly ash and no silica fume. If you look at the 385 that I put in red, this is to underline that with a super workable concrete, your concrete does not to be as fluid, so you can save quite a bit on the binder, you can save quite a bit on the paste. So if you were to say 385 kg per cubic meter, that's about 650 pounds per cubic yard. So the mixture is also more robust and tolerates more variability in moisture content of sand or temperature or super demand. Otherwise, the difference is that with the SEC, you need a smaller aggregate. So we're using the 3/8-inch aggregate versus the super workable is using half-inch aggregate, and you have more sand. So you reduce the amount of coarse aggregate, you increase the amount of sand to maintain the same mortar content. So both of them are air-entrained concrete. You can see the fluidity is very different. So this would be about 30 inches. I'm converting on the fly here. This is about 20 to 22 inches slump flow. We tested a variety of fibers. Dr. Nassif presented a very nice study that went very extensively into various types of fibers and synthetic fibers. Here we did want to use steel fibers. So we have steel fibers that we call a macro fiber. Those are hook end fibers, Becquerel fibers, 30 mm. And then we also decided, because we would like to not only control the macro cracks, but the micro cracks like we do with UHPC. So combine microfibers that are ½ inch in length with the macro fibers. So it's a ratio is macro to micro is about 80% to 20%. Mass or volume is the same. And we also wanted to look at the performance of synthetic fibers. So we have polypropylene fibers. And then we have a fiber that is quite unique, that is a hybrid steel and polypropylene fibers. So from a mixture proportioning point of view, you've probably read about this. When we design fiber reinforced concrete, you want to maintain the thickness layer of the mortar to be the same. So when you have fibers, the thickness of the mortar needs to be the volume of excess mortar divided by the surface area of the coarse aggregate, in this case gravel, plus fibers. So by doing that, and then you can improve the workability of the concrete, which means when you add fibers, you have to reduce the coarse aggregate and you have to increase slightly the sand content. So if you look at the performance, in this case, 4-point bending of fiber reinforced concrete, well, in blue over here is the SCC without any fibers. As expected, you reach the peak and then you lose ductility. The polypropylene fibers, as expected, also you lose a lot of ductility, but it gives you good residual strength at very high deformation. But the performance we're really looking for is this performance. The top three figures are all with steel fibers, whether it's only the 0.5% single steel fiber or the 0.5% combination of micro-macro. You can see that the performance is very good, elastoplastic, a lot of ductility, and you want that in your bridge deck because eventually it will crack, and you want the load carrying capacity to be maintained. We also did the crack mouse deflection versus a single point loading in the middle with a notch end. And as you can see, the steel fibers again gave you a lot of residual strength, a lot of ductility, a lot of fracture toughness. So this decision was to use the combination of micro-macro steel for rehabilitation of this bridge. I also failed to mention maybe all of these mixtures have 4% type G expansive agents. So this is calcium oxide base that reacts with water and forms calcium hydroxide and gives you expansion at very early age. So this is a drying shrinkage of specimens that are moist cured for 7 days. And you can see here for 7 days you have expansion because of the hydration of the calcium hydroxide. And then after that you put them at 50% humidity. And then you start having some shrinkage. So this is shrinkage compensation. But if you only use SCC without any, you would have about 750 microstrain. This is after 1 year. And if you use the shrinkage compensation, you can reduce that quite a bit, by at least half. Okay? And another thing that is not shown here, but we showed it in the study, is that the early age expansion due to the calcium hydroxide puts the steel fibers that are rigid in compression, and that gives you local pre-stressing effects, thus reducing the tensile stress of the concrete. All right, so we also did some limited flexural test and shear testing, but this is we also looked at how much steel we can reduce by adding fibers, but I'm not presenting this here. So the same amount of steel, adding 0.5% of the 2 steel fibers. And you could see here the load deflection behavior. So in orange, you have the SCC without fibers. and the 0.5% fibers, the two type of fibers. Again, we selected the one in gray, which is a combination of micro-macro. So the next step was the fun part, to go to the job site and try to implement this, quite new concrete with job site conditions. We did this in Missouri in the summer, not very friendly construction environment, it's pretty hot. But you can see here the roadway, so this is 30 feet and two spans, about 120 each. So the pre-stressed girders. And as expected, in the middle where you have the diaphragm, there was also, this is where the casting actually started, and then it went above to the bridge deck. We expected a lot of positive moments. You'll see the numbers later, you'll be surprised how high they are. So both in the longitudinal direction, we expected a lot of negative moments in the deck. And again, the deck, whether it's the top or the bottom, it's in tension. And in the lateral direction also, we expected quite a bit. And we did some SAP 2000, 2D, 3D, finite element, and we predicted all the values. So the decision was to use the fibers, but also to increase very slightly the expansive agent from 4% to 5% to mitigate further the shrinkage. So again, half-inch maximum size aggregate, 30% flat fly ash, expansive agent 5%, polycarboxylate VMA. Actually, that was interesting because initially we did think that we could manage to cast that concrete with a 20-inch slump flow. But you'll see later that we were not able to because there's a slope of 2 to 3% on the bridge, the crown. And then when we did some of the trials, started kind of, it was not exotropic enough. So we had to relax a little bit the slump. So it was highly flowable. But the VMA was still there to give it more robustness. Did quite a bit of trial because our mixtures in the lab were developed with one admixture supplier, and the contractor hired a concrete supplier that had other admixtures, other materials. That's part of any project. You have to go and work with them for a couple of days. And they got it right. It was just very good. And for the mock-up, this is a mixture. So you can see that a type 1-2 cement was 30% fly ash, some expansive agents, water to binder ratio 0.42, half-inch aggregates, river sand, and then the ST fibers, 80%, 20% microfibers, and the 3 chemical admixtures. Not a very easy mixture to implement, but the concrete supplier got it right. We did a mock-up, learned a lot. It was a very hot day also for the mock-up. Had some initial issues with finishing. It was pretty viscous, sticky surface. But using different finishing agents, finally the contractor was able to finish a mock-up very nicely and give it the texture that is needed for the bridge construction. All right, so the next step was doing this on the job site. Again, this was done in the summer because of the temperatures. It was decided to do the work at night. So the first pour started at midnight and finished by 8 o'clock in the morning. And we expected a lot of tension, as I said, in the upper deck, vertical, not up and down, but longitudinal and transverse directions. So we put 6 baskets with instrumentations. This is a data acquisition system over here. It's connected to solar panel with a cell phone to download the data in real time. And these are the baskets, and there are 3 sets of sensors. You have thermocouples, you have embedded strain gauges, and you have relative humidity sensors. Some of them we had to design in-house, like the relative humidity sensors, and we put them at 3 levels. As you can see, the bridge deck is 8.5 inches, so they sat at 3 different levels. And that was actually, it was very important to do that. If you ever have to do this, do that as a last stage before construction starts, before concreting. So they basically gave us about 6-7 hours. There were like 240 wires that had to be connected from the bridge deck all the way to where the data acquisition system, and we were almost concreting at the same time as we're installing the sensors. Because if you do that ahead of time, often they get broken down from construction traffic. So as I said, the construction took place at night. We did specify a certain temperature, and we had ice just in case the temperature was high. But the concrete pumped very well. Again, this is 40 kilogram per cubic meter. So kilogram per cubic meter of steel fibers. It plays very nicely. There was a little bit of a learning curve in terms of finishing, but after a few trucks, I think the contractor got it right. It was very easy to consolidate, very easy to finish, surprisingly. And then the texture and the moist curing was specified for 7 days. And you can see the texturing. We had many graduate students on site. This is great learning opportunities. Managed to take my son even, last minute, he's a ceramic engineer. Hey, let's go, I need one more person. And all the testing was done at the end of the pump. So at the end of the pumping, we took samples from various trucks and we tested them. Missouri DOT had their own lab, third-party lab, and the contractor also had his own third-party lab. So three sets of labs. We sampled many trucks, so truck number 2 all the way to truck number 40. You can see this is 1 hour after start of placement, 6.5 hours later. The first 2 trucks showed high temperatures. You see the concrete temperature 97 degrees Fahrenheit and 91. So the specification was for a maximum temperature of 32 degrees Celsius. So we had to, which is 88, we had to put ice. So the trucks from 12 all the way to 40 had ice. Replacement of some of the water was ice to control the temperature. You see the slumps, initial slumps, they varied between 6 and 10 inches. So they are not your 20-inch slump flow, but they're extremely flowable and very easy to pump. They were all air entrained. We took samples after 1 day, about 100 miles away, where the university is in Rolla, and subjected to the concrete to a lot of testing. And these are some of the test results. Compressive strengths at different ages. In parentheses, you have the coefficient of variation. And when you sample something on the job site, anytime you're less than 5%, it's really excellent. So that means the concrete cylinders were properly sampled and prepared and transported and cured. This is all moist curing after getting them to the lab. So again, you don't need to have very high strengths. We're talking about strengths of 8,000, 7,500, 7,000 psi. It's the durability that matters. And in this case, a shrinkage. So elastic modulus, flexural strength, shrinkage. We took shrinkage samples. These are averages, each of them of 3 prisms. We took them from 3 trucks and again subjected them to 7 days of moist curing after 1 day. So 1 day of demolding and then moist curing. And you can see that the expansion of the calcium oxide. Now we got about 100 microstrain less than the 4%. So that was a good strategy. Okay, this is a bit busy, but if you look at these baskets, I'm only showing the results of basket number 1. And this is interesting. This is showing the reduction of relative humidity. But on top, you have 100% relative humidity, and about 3-4 months later, it goes to about 80% in cementing. We followed the behavior of that bridge for about 4.5 years. So 80% cement continues to hydrate up to 80%, but it drops. Temperature, you have the temperature, but the strains were very high. So they vary here from a low of 500 microstrain to a high of about 1,100 microstrain. So 1,100 microstrain in tension, concrete has cracked for sure. But then we kept sending students and working with the Missouri DOT crew to look at crack distribution. And as expected, there were some micro cracks. We call those hairline cracks. They were very, very small around the middle diaphragm, about 10 feet in each direction. But beyond that, there was no cracking, very little pitting of corrosion on the surface. The surface is how it was cast, after screening, so it's a very nice surface. And I go there a couple of times a semester when I go to visit MoDOT, and I stop and put my hard hat and take a look, and it's doing very well. So as I said, we did also some finite element analysis, and I don't have a lot of time to go through this, but briefly, we wanted to know what is the autogenous shrinkage after 1 day, because our prisms were demolded after 1 day. There was already some chemical shrinkage, some self-desiccation. So we wanted to know that, and we also wanted to know how much load was being carried by the corrugated steel. So, and when you cast the concrete on the corrugated steel, you don't expect anything to be supported by the girders. So indeed, it was zero. But later we found out that if you go up to about 260 days, then all the load is really carried by the pre-stressed girders. So there was some analysis done in that from the finite element analysis and the sensors at different levels at different ages, knowing the temperature variations, knowing the shrinkage. We calculated the autogenous shrinkage to be 75 microstrain, which is very reasonable. It confirms the results we had in the lab when we developed mixes like that. We also were able to determine what the K factor. So all in all, it was a very successful project. I think MoDOT learned a lot, and now they have special job provisions for redecking using highly flowable fiber-reinforced concrete. They are not afraid, Annie, to use steel fibers. They embrace it, actually. And as we speak, we have 2 bridges that are being rehabilitated using thin bonded UHPC overlay. These are non-proprietary UHPC overlays that are 1.5 inches. Right, very good, thank you.